Solve the linear program below using Simplex. Maximize z is equal to 2x sub 1 plus x sub 2 minus 3x sub 3 plus 5x sub 4, subject to x sub 1 plus 2x sub 2 plus 2x sub 3 plus 4x sub 4 is less than or equal to 40. 2x sub 1 minus x sub 2 plus x sub 3 plus 2x sub 4 is less than or equal to 8. 4x sub 1 minus 2x sub 2 plus x sub 3 minus x sub 4 is less than or equal to 10, while x sub 1, x sub 2, x sub 3, and x sub 4 are all greater than or equal to 0. In this problem, we are given a linear program in standard form, where all constraints are of the less than or equal to type, with a positive right-hand side, with 4 decision variables and 3 constraints. We begin by adding a slack variable for each constraint. Then, n minus m variables are set to 0, where n is the number of variables, both decision and slack variables, and m is the number of constraints. These are our non-basic variables. Conventionally, we prioritize decision variables first in selecting the initial non-basic variables. In this case, n is equal to 7 and m is equal to 3. So we will have 4 non-basic variables, x sub 1, x sub 2, x sub 3, and x sub 4. The remaining m variables are the basic variables s sub 1, s sub 2, and s sub 3. Knowing this, we can now set up the starting tableau. Iteration 0. Build your own starting tableau by making an m plus 1 times n plus 1 table, where the first row represents the objective function and each succeeding row represents a constraint. The columns are labeled as variables except for the last column, which is labeled as RHS, or the right-hand side of the constraint. Each row is filled out by entering the corresponding coefficient of each column's label. For the RHS column, we enter the right-hand side values corresponding to the constraint that the row represents. Note that for the objective function row of the initial tableau, each entry is the additive inverse of the corresponding coefficient in the objective function, and the RHS column entry is 0. Now we can proceed with the Simplex algorithm. For each iteration, we apply the optimality condition, which is used to determine the entering variable, the non-basic variable that will become basic, and the feasibility condition, which is used to determine the leaving variable, the basic variable that will become non-basic. According to the optimality condition, the entering variable is the most negative entry in the objective function row of a maximization problem, or the most positive entry for a minimization problem. Since this is a maximization problem, the entering variable is x sub 4 with an entry of negative 5. The column of the entering variable is called the pivot column. Next, we apply the feasibility condition by finding the row with the smallest non-negative ratio of RHS to pivot column entry. This row is called the pivot row. The intersection of the pivot row and pivot column is the pivot element. The leaving variable is s sub 2 with a ratio of 8/2 is equal to 4. Knowing the pivot row and pivot column, we normalize using the following Gauss-Jordan operations. Row 3, r sub 3 prime is equal to r sub 3/2. Row 1, r sub 1 prime is equal to r sub 1 plus 5r sub 3 prime. Row 2, r sub 2 prime is equal to r sub 2 minus 4r sub 3 prime. Row 4, r sub 4 prime is equal to r sub 4 plus r sub 3 prime. Note that we always perform first row operation in the pivot row, since the new value in the pivot element will be used to zero out all other values in the pivot column. After normalizing our values in the pivot column, we arrive at iteration 1. Thus, for the next iteration, our basic variables are x sub 4, s sub 1, and s sub 3, while our non-basic variables are x sub 1, x sub 2, x sub 3, and s sub 2. We arrive at the tableau for the next iteration by swapping the pivot row variable s sub 2 for the pivot column variable x sub 4. Gauss-Jordan row operations are used to normalize the tableau such that the pivot element has an entry of 1, while the other entries in the pivot column are 0. This is the tableau for iteration 1. We repeat the process of finding an entering and leaving variable for every iteration until the solution becomes optimal. For this problem, the Simplex computation ends at iteration 2, with basic variables x sub 2, x sub 4, and s sub 3. The value of a basic variable at any iteration is its corresponding RHS entry, and the value of all non-basic variables is 0. Therefore, the optimal solution to the problem is x sub 2 is equal to 6, x sub 4 is equal to 7, s sub 3 is equal to 29, x sub 1, x sub 3, s sub 1, s sub 2 are all equal to 0, with z is equal to 41.